So the objective of this lesson is to basically understand the basic concepts from the rational function segment. So let's say, firstly, what is a rational function? Now, when you have examples of the form, let's say 2x plus 3 over x minus 5. Now, where you can see that you got a function in numerator and function denominator, anything of the form px by qx, which you can't further simplify, and that can be referred as a rational function. And what we have to understand is some of the key terms that are really linked with this particular part. Now, rational functions are basically, you can identify them with the vertical asymptotes, horizontal asymptote. We'll have something called a sketching of the function, sketching that is asked. Then you got the roots of the function, y-intercept, and then also the basically the composition and inverse of this function. So composition and inverse. So what I'm going to do is I'm also going to take Sine diagram. So Sine diagram also, like, just understand how we use Sine diagram to categorize and understand the rational function. So let's go ahead with firstly the vertical asymptote. What is the vertical asymptote for rational function? How do you find that out? Now, to find out the vertical asymptote, you remember that you always equate denominator to 0. So denominator, if it is 0, now, for example, anything over 0 is infinity. So what makes the function undefined is referred as a vertical asymptote. Now, x belongs, basically, when I say x minus 5, it is equals to 0, so I get x is 5. So if I plug x is 5 here, if you see in this question, what happened is that the entire denominator becomes 0. Now, since the denominator becomes 0, it becomes undefined. So that's the place where you got the vertical asymptote. Now, for horizontal asymptote, actually, there are multiple ways you can think of. Now, for horizontal asymptote, you can just do one thing is there are two different ways. First thing is I can take, let's say, if you got ax plus b over cx plus d, the shortcut ways that you could just take the coefficients like here a and c. So I could take a over c as the horizontal asymptote. Now, what happened is that actually concept of horizontal asymptote is when x is infinity, positive infinity, or x is negative infinity, what's your y value? So that's the horizontal asymptote. Now, for example, for this question, if I got, let's say, y equals to, let's say, 3x plus 2x plus 3 over x minus 5, and if I take x is, let's say, infinity. Now, what happened is that if I take, let's say, x common from here, I get 2 plus 3 over x. And if I take x common from here, it is 1 minus 5 over x. So this x and x get canceled. And as x tends to infinity, you will notice that that 3 over x and 5 over x will tend to 0, because anything over infinity is 0. So this part becomes actually 0. So that's why answer is 2 over 1. And here you can see that it's the same answer you're getting with the shortcut as well. So 2 over 1. So for horizontal asymptote, what I recommend is that you show this working. You take the leading power x common. I'm going to take more example, of course. Like, for example, I've got, let's say, x squared plus 7x minus 3, or x squared 2x squared minus 5x plus 7. So here the leading coefficient is x squared, and here it is x squared. So the coefficients of them ratio is the horizontal asymptote. So here the horizontal asymptote I know is y equals to half. But how does it come? So if I take x squared common here, what I get is in the bracket, you get 1 plus 7 over x minus 3 over x squared, and over, if I take x squared common from here, I get 2 minus 5 over x plus 7 over x squared. So this part becomes basically 0, and then this get canceled, and the answer is half. So that's how you find out the horizontal asymptote. Now, as far as the other rule is concerned, that if your degree of numerator is lower than degree of denominator. Now, what I mean to say is, if I've got something like 5 over x minus 3, now you can notice that when x tends to infinity here, this entire expression tends to 0. So that's where you get y equals to 0 as the horizontal asymptote. So you got these two different rules, that once your degree of numerator and denominator is the same, which is y equals to a over c. Now here, if you have like a quadratic over quadratic, it is half. And if you got degree of numerator is lower than degree of denominator, then y equals to 0, which is x-axis, is always the horizontal asymptote. So that's the concept linked with horizontal asymptote. I think the third case is, what if your degree of numerator is higher? Like for example, you got x squared plus x plus 3 or x minus 2. So in that case, you will have something called as oblique asymptote, which is only for the higher level students. So I'll cover that part in the next series. So first thing is that let's just quickly understand this question that we started with. So here my horizontal asymptote that I found is actually nothing but y equals to 2 over 1 actually. So if you see the horizontal asymptote at this stage, I'll just quickly erase this out. So the horizontal asymptote is y equals to 2 and let's do this. So the horizontal asymptote here is y equals to 2. So now coming back to the something called a sine diagram. Now to draw the sine diagram, actually sine diagram gives a fair picture of which part of the graph is above x-axis and which part of the graph is below x-axis and all. So when you're finding out, let's say sine diagram, so what happened is that, okay, let's say here is the simple, like, vertical asymptote. So you take x equals to 5, you mark that, as well as mark the roots. So for the roots, you equate the function to 0. So if I equate to 0, so you get x is negative 3 over 2. So that's your function roots. Now what you do is you pick up a value in each range. So if I pick up, let's say 6 here, so if I take 6 here, it's going to be positive over positive. So it's positive 6, positive out here. Now if I take a value, like for example in between, I could take x as 0, so it is like 3 over negative 5 in that case. That's negative. Now if I take anything here, like for example x equals to negative 2, so that's you're going to be negative 4 plus 3, that's your negative 1, or negative, so that's going to be positive. So what does it mean is that your graph is here positive. It means that graph is above x-axis here. Here in between negative 3 over 2 and 5, so it is below x-axis. So you got x-intercept, y-intercept, which is, so x-intercept was negative 3 over 2, vertical asymptote at 5. And so you got x equals to 5, the vertical asymptote. Draw this as a dotted line. And here it is 3 over negative 5. So 3 over negative 5 is this here, y-intercept, which is this. So now if you draw horizontal asymptote y equals to 2 somewhere here. So this is y equals to 2 is the graph. Now you got to make sure that your graph passes through like here, and it is parallel to the horizontal asymptote. Then it passes here. It is like this. And in this case, it is going to be here, because if it is here, then you will get another root. So that's why it is not here. And also if you look for the sine diagram, at negative 3 over 2 and at 5, here it was positive. It means the graph is entirely above x-axis, and this one rules out. So this is how your graph looks like approximately. I'll just draw a smooth curve here. So in this case, the graph is something like this. It is obviously negative 3 over 2 is here. So for this question, actually, if you look at the domain of this, is x belongs to real numbers and x should not be 5. And range is y belongs to real numbers and y should not be equals to 2. Provided it is a natural domain. Now, provided it is a natural domain. Sometimes, okay, now if the question the question is, let's say if I have f of x is, let's say 2x plus 3 over x minus 5, and the domain of this function is, let's say, x more than 7. Now, for this domain, can you find out the range of the given function? So what happened is that in that case, what I take is x equals to 7 is here somewhere, and they are just taking this part of the graph. Okay, so they're just taking this particular part of the graph. So for that, I'll have to just find the y value, which is, if I plug x is 7 here, I get 2 times 7 plus 3 over 7 minus 5. So 14 plus 3 is 17 over 2. So this is 17 over 2. So this part is basically for this, the range will be y between 17 over 2 and so this is 2 is lower number, so 2 to 17 over 2. So that's going to be the range of this function. So just be careful as far as the domain and range is concerned. So let's take one more example for doing the rational function sketching. So here's another question. Now let's take y equals to, let's say, 5 minus 7 over x plus 2. So now let's say I wanted to find out the equation of vertical, horizontal, and the root, sine diagram, and everything, and then finally sketch this graph. So here what we do is, it's a little different form. Now when you're finding out the equation of vertical horizontal asymptote, some students tend to take the LCM of this, which is like 5x plus 10 minus 7 or x plus 2, and that reduces back to the normal standard ax plus b or cx plus d format, which is like 5x plus 3 or x plus 2 here. So now if you find out the vertical asymptote, equate denominator to 0, so you get x equals to -2, and horizontal asymptote is y equals to 5, because that's the coefficient of x that I'm looking forward to. Roots are basically, root is basically here -3 or 5, and when you're finding out the y-intercept, it is 3 over 2, and no need to draw a Sine diagram if they have not asked so. So just quickly now, if you sketch the final graph here, the final graph is, now we'll just quickly mark the values here. So you've got x equals to -2 as the vertical asymptote. So here x equals to -2, this is the vertical asymptote now. So this is x equals to -2. Horizontal asymptote is y equals to 5. So y equals to 5, you take this here. And what we got is the root is at -3 over 5. So -3 over 5 is here. And y-intercept is +3 over 2. So the graph out here is already, you can see that this is how it is going to be here. And since you got there, the graph this side is here. Definitely, because then if your graph here or something, then you have got another root, which is not possible because you just got one possible root, which is -3 or 5. So for this question, when you're sketching the graph, the domain of this function is x belongs to real number, x should not be -2, and y belongs to real numbers, y should not be -3, -5. I mean, y should not be equals to 5. So this is the horizontal asymptote. So this is the part of sketching now, and let's get started with some of the inverse function questions on the rational functions. So when you're taking the inverse function of rational type of questions, let's say if you got f of x is 2x plus 3 or x minus 5, okay. Now, the first thing that is important is that you specify the domain and range for the original function. So here domain is x belongs to real number, x should not be 5, and range is y belongs to real numbers, y should not be equals to 2, because that's your coefficients here. Now, the equation of vertical asymptote is x equals to 5. Equation of horizontal asymptote is 5. Horizontal asymptote is y equals to 2. Now, when you're finding the inverse, the step procedure is that you interchange x with y and make y the subject. Make y subject. And graphically, it is nothing but reflection y equals to x line. So now what we do is, if I have to find out the inverse function for this one, here what we do is, you can quickly write down this as y equals to, let's say, 2x plus 3 over x minus 5. Interchange x with y, so it is 2y plus 3 over y minus 5. Make y the subject now. So I'm going to just cross multiply. So xy minus 5x equals to 2y plus 3. Now you bring y terms one side. So xy minus 2y equals to 5x plus 3. So y x minus 2 is 5x plus 3. So y is equals to 5x plus 3 over x minus 2. So that's your inverse function here. So for this inverse function, if you look at the domain here, x belongs to real numbers, x should not be 2, y belongs to real number, and y should not be equals to 5, and which is exactly the like the flipped version of this. So here it was y not equals to 2, here it is x not equals to 2, and here they said that the range was domain was x not equals to 5. Here the range is y equals not equals to 5. Now, this is how you find the inverse function. And now when you graphically wish to sketch this, you first need to sketch the original function, which I'm just quickly assuming that you have understood previously. So I'm just quickly actually going to show you on the GDC. So let's just do the question on GDC here. So now when you wish to see how the sketch of this look like, what I'm going to do is quickly, I'm just going to sketch it under the graph function. So I'm just quickly inputting into the graphs. So let's say this is my, I'll just delete these functions. So we got now 2x plus 3. So 2x plus 3 over x minus 5. So x minus 5. So this is the function here. Now, just make it the standard window so that you can see the graph entirely. Now, this is my original function, you can see. Now, if you wish to sketch this inverse of this function, you can just draw y equals to x line. And now, if you just say sketch inverse, it asks which function you want to sketch. Okay, so I want to sketch inverse for this. So you can clearly see that this is the green one is the reflection in y equals to x line. It's not a square grid, so you can't see that. But actually, when you sketch this on a square grid, you can see that they are actually inverses of each other. Now the same thing if I can show you on the Desmos as well. So here the function was basically y equals to, let's say, y equals to 2x plus 3, 2x plus 3 over x minus 5 over x minus 5. So this is my function here. If you see, the inverse of this function was 5x plus 3 over x minus 2, and the original function was 2x plus 3 over x minus 5. So you can clearly see that actually it is getting reflected in y equals to x line. So this red part, actually this part of the graph got reflected here. This part of the graph, which is here, got reflected here. So this is how you find out the inverse function of the rational functions.